Okay, so let me go find these slides, please.
Do that. It should be all right.
I can't find this presentation. Give me a few minutes, guys. Sorry about that.
I was at the yacht back then. I got there. We found the blood that shell. Inside it, we found the child remains of our body. That same body.
Ah, okay, here we go. All right, I should show you this one here. So this slide here is important because it explains one of the important steps in the Dijkstras algorithm. I mentioned this already. It's called the relax step. Now here is what you need to know. It says that if at any given time, let's resume share. Okay, you see it now?
Yes.
Yeah.
Okay. So if at any given time, the numbers here are assumed to be the length of the shortest path from some source vertex to those vertices. Okay, so let's assume that at some given time, the distance from S to U is 5, and the distance from S to V that we figured out so far is equal to 9. What this tells you is that if these two guys are connected by an edge of length 2, after the relax step, this one would become 7. Why? Because now you would have discovered, so source is somewhere here, and the length of the shortest path to this guy is 5. The length of the shortest path to V is 9. But because you know this edge now, you've seen this edge, If you relax this edge, then you're going to know that there is a better path from S to V that goes through U, and that's what this relax step takes care of. So by the end of this relax step, you would have updated the length of the shortest path to V. Another example of the relax is, let's say that your information says that the length of the shortest path from the source to this guy is 5, and the length of the source to this vertex is 6. And let's say that you suddenly saw this edge going from U to V of length 2. When you do the relaxation, it is not going to change the length of the shortest path to V, because if you were to use this 5 plus 2 as 7, it's not going to give you a better path. And so therefore the relaxed step will leave this as 6. So a relaxed step essentially takes care of an edge, processes an edge, and makes sure that the length of the shortest path to both ends of that edge are meaningful, in the sense that they don't contradict each other, or you have taken that edge into account for all possible shortest paths. And what Dijkstra does, Dijkstra's algorithm does, is it starts from a source and then works its way outside, expanding out from the source, and does a relaxation of all the edges as you go out. And it relaxes the edges in the order in which the vertices get visited. So remember, the vertex gets visited when you pull it out of the priority queue, and the moment you pull it out of the priority queue, you go and relax all the edges that are incident on, that are going out of that vertex. So that's what you do in the Dijkstra's algorithm. When you have negative edges, it's going to do interesting things. If this were -2, what would happen when you relax? What do you think this value is going to be? If this value were -2, what do you think will happen?
Wait, you said it was -2?
Yeah.
3?
So it would become 3, because 5 minus 2 would give you 3. And so this new value would be 3. What about here?
Three as well?
For here as well, it would become, instead of 6, it would become 3, because 3 is better than 6. If this had been 1, then it would not change. Then it would leave it as it is. So the relax step does exactly the same, even if there are negative values. However, it messes up Dijkstra's, because the order in which the priority queue is processed is not guaranteed anymore. And that's why you need Bellman Ford algorithm. The Bellman Ford algorithm simply does relax of each edge many, many times. And it doesn't have a very good order in which it does these relaxations. So it does something very simplistic. It just goes and relaxes all the edges n times. So that's why the time complexity is number of edges times the number of vertices, because every edge gets relaxed in every iteration, and there are n iterations. What Bellman Ford showed is that if you do this, if you relax an edge n times, and if you do this for every edge in the graph, you will get the length of the shortest path from source to every vertex that you want. And that's why Bellman Ford algorithm works. So let me move forward here. This is the Dijkstra single source shortest path algorithm. Here's an example. I won't go through this. You can look through this. Now, what's important for you to understand is that Dijkstra's and Prim's algorithm are closely related. Now, let me remind you that Dijkstra's algorithm and Prim's algorithm solve very different problems. Dijkstra's algorithm is for single source shortest paths, namely from a single vertex, it finds the length of the shortest path to every other vertex. Whereas Prim's algorithm does what?
Finds the minimum spanning tree.
It finds the minimum spanning tree. So even though they're a little bit different, their algorithms turn out to be somewhat similar. Both of them use priority queues. Both of them do some initializations and then have a simple while loop and in each iteration of the while loop, it does an extract min. And then it has something like the only difference is that in the Dijkstra's algorithm, you do what's called as a relaxed step. In the minimum spanning tree algorithm, you do something slightly different. In Dijkstra's algorithm, you process the distance values. In Prim's algorithm, you simply decide which vertex, which vertex the new vertex is going to be connected to, and that's what happens over here. But the time complexity is the same. The general structure of the algorithm is the same. The only thing that's different is what happens here. Here you check if dv is bigger than du plus weight of uv. Here you check if weight of uv is less than key of v. So what is important to understand here is that in Dijkstra's algorithm, the priority values are the distance from the source to that vertex. In Prim's algorithm, the priority values are simply the length of the shortest edge that connects to the spanning tree. So it's simply the weight of the last edge that you have on the path. So that's why you don't do cumulative stuff. You only check the weight of the last edge. So you check whether the weight of the last edge, which is uv, and check whether it's smaller than whatever it is you've found so far. If it is better, then you connect it. Otherwise, you don't. So it's important to really understand this close relationship, because then it's easy for us to understand some variants of these algorithms. Any questions about this?
They both produce trees, right?
They both produce trees, but this tree is called a minimum spanning tree. This tree is called a shortest path tree.
And the root is the source.
And the root is the same.
Vertex.
It's the source vertex. That's right, in both cases. Now, the question is, why would they be different, right? And it turns out that there are examples where it can be different. And we could work out this example if you wish. Does anyone know the answer why a shortest path tree would be different from a minimum spanning tree?
And we didn't find a sadness on this thing. That's because he wasn't looking for it. I'm pretty sure we'll go back to here.
All right. So let's work out an example, and maybe we can see this. But let me see what else I have next. I'll skip this part. Oh, I do have some slides on negative edges. So let's go through this before we talk about why shortest path tree is different from minimum spanning tree. So here's an example of where Dijkstra can fail. One of you asked this question: what happens if you have negative edges? So here's the example. It's from this book by Kleinberg and Kardosh. So let's assume this is my source, right? So what happens? First, the priority queue has all the vertices, and the source will be at the top. It will have the highest priority, and then you will change the priorities of both U and T. T will have priority value 1. U will have priority value 2 because you've processed these two edges and you've relaxed them. After that, what's going to happen? Remember, this edge is coming in this direction, so you're not going to be able to process this. So you will now, because T is the next, has the highest priority once you've removed the source, this gets processed first, and the distance for this would be a 1. So you would report the length of the shortest path from S to T to be 1. On the other hand, eventually you'll figure out that the length of the shortest path from S to T is actually 2 plus 3 plus minus 6, which is -1. So the answers that you will get by using Dijkstra would turn out to be wrong. Does that make sense?
Yeah, that makes sense.
So there are some things that you could do, making weights positive, adding a constant. So you know, one idea that you might think is, what if we added a big, what if we add 6 to everything? That way you will have no negative numbers, right? It turns out that that doesn't work for you for a variety of reasons. Again, there is the example here, and you're welcome to take a look at this later. If you add, so in this case, I've added +3 to, so imagine that you have a network with 2, 3, 2, 3, and -3. And let's say you add 3 to everything, because the most negative number here is -3. If I add 3 to it, 2 becomes 5, 2 becomes 5, 3 becomes 6, 3 becomes 6, and -3 becomes 0. What if I worked with this graph now, because it has no negative edges, and run Dijkstras? It turns out that, again, Dijkstra will give you wrong answers, because it would say that the length of the shortest path from here to here is 6. It would say that the length of the shortest path from here to here is 10, because this is a longer path. It's 6 plus 6 equals 12. But in reality, this is the shortest path from S to T, because it's of length 3 minus 3 plus 3, which is +3, whereas this one is +4. Okay, did that make sense? Do you want me to explain this again?
No, that makes sense.
Others? Anyone else?
Yeah, I'm good.
You're good. Okay. All right. If I don't hear from anybody, let me move on. Yeah, so here is the Bellman Ford algorithm. It simply says, it finds the length of the shortest path from the single source to all vertices, except when you have a negative cycle. So Bellman Ford also will not work if there is a negative cycle, but it's okay if there are negative edges. Now, why would Bellman Ford have a problem when there is a negative cycle?
So if there is a negative cycle, you can't really define the shortest path, since you can do it in any number of times.
That's right. If you have a negative cycle, the length of the shortest path between any pair of vertices on the negative cycle is a mess, because in order to go from A to B, I could simply go over the negative cycle multiple times, and I could decrease the length of the shortest path over and over and over again until it becomes negative infinity. So negative cycles are a no-no as far as shortest path problems are concerned. So, but one good thing about Bellman Ford is that if it detects a negative cycle, it'll report failure and stop. The basic idea, as I said before, is to simply relax the edges over and over again until you get the correct answers, or it fails because it detects a negative cycle. The real question is, how many times do you have to relax an edge? And as I said before, it relaxes it n times. Here's an example of a negative cycle. And what you see is that the distance between any pair of vertices on this negative cycle is basically negative infinity, because you can simply repeatedly go over this and it'll go down. From going from here to here would be 7 plus minus 4, which is plus 3. But if I do it one more time, then it would go down even more, because I would get 7 plus minus 4, that's 3. 3 minus 6 would be negative 3. Negative 3 plus 7 would be plus 4. Plus 4 minus 4 would be 0. So just by going over it one more time, it became 0. If I do it one more time, it'll become negative 3, and so on and so forth. So that's the problem with negative cycles. What else do we have?
Professor?
Yeah.
Can I try to answer the question you asked?
Yes.
Is it because the MST it doesn't do the relaxing, it just gets the edges once?
Sure, but do you have an example? Can you build an example where these two are going to be different?
Oh, no, I didn't think of an example. Okay, I'll work on that.
Give it a thought, yeah. So here is Bellman Ford, very, very simple algorithm. It simply does the relax of every edge, and it does that many, many times. And if it ever finds that the value still keeps decreasing, then it will simply say that there is a negative cycle and it'll fail. Otherwise, it will stop and give you the right answer. So that's Bellman Ford for you. So this guy allows negative edges, but does not allow negative cycles. And here's an example of a Bellman Ford example. There are some negative edges, but there are no negative cycles. And you'll see that Dijkstras would simply have said, here's the shortest path, or this is the shortest path from S to Z. But this guy will figure out that the shortest path goes all the way around, which Dijkstra would never have figured out. Sorry, Dijkstra would have figured out this, but actually the right answer is, no, that's the right answer, sorry. Yeah. So anyway, Dijkstra would not have worked because there are negative edges. If you apply Bellman Ford, it will eventually figure out that this is the shortest path tree for this particular example. By the way, it is important for you to understand that in this example, the dark edges correspond to the shortest path tree. Okay, so the shortest path tree from the source vertex has this edge, this edge, this edge, and this edge. If you were to do a minimum spanning tree, what do you think you'll have? So you will have this edge of length 5. You will have this edge of length 2. You will have this 3 will probably get, let's see, what else would change? Well, in this case, it looks like it won't change. It'll be also the minimum spanning tree. So maybe it's okay. So back to this example here. We are now ready to talk about the Allpair shortest path, but if there are any questions, I'd like to answer those first.
Quick question. So in
Yes.
the Bellman Ford, we have
Yeah.
to relax the edges n minus 1 times.
Correct.
Why is that right?
So here is the general idea. If there exists a shortest path from A to B for any vertex A and B, and if there are no negative cycles, then that path will have at most n minus 1 edges. Because, well, actually, it'll if you in the worst case, it'll have n minus 1 edges, because you cannot have any vertex repeated, right? So therefore, that path can only have n-1 edges, which means that if you relax this first edge and then the second edge, then the third edge, then the fourth edge, if you relax each of the edges on that path once, you should have, and if you do it in that order, you should have the length of the shortest path from source to that vertex. So therefore, you never have to relax anything more than n-1 times.
Okay,
that
so
make
like
sense?
because there is no negative cycle, adding any
Correct.
more edges will just make it bigger. That's like a
Correct.
Okay, that
Exactly.
makes sense.
So if the length of the shortest path is only 1, okay, then once you relax the source, the first vertex, in the next iteration you would have relaxed you would have relaxed this edge, and you would have taken care of the correct value for this guy. So so if you start with the correct distance for one vertex, all its neighbors would eventually have the correct value for the distance after you relax those edges. So therefore, since you already know the length of the shortest path from source to itself, which is 0, it cannot be negative because there are no negative cycles. So the length of the shortest path from source to itself is 0. So you already know that the distance value for the source vertex is correct. So therefore, in the next step, all its neighbors would have gotten processed, and anything that's only one edge away in terms of the shortest path would get its correct value. Then anything that's at distance 2 edges away, all those will get those to be correct in the next iteration. And you have to do this at most n-1 times, because there is no path of length more than n-1 edges.
Gotcha. That makes sense. Thank you.
Yeah. So the relax is pretty powerful. In fact, n-1 is already being generous. In most cases, you won't need n-1 rounds. You would probably figure out earlier, and you can put in some tests in there to see if none of the values are changing, you can stop. Okay, so we are now ready to talk about Floyd-Warshall's algorithm. There are actually 2 different versions of Floyd-Warshall algorithm, and it's very useful to understand both of them. Well, actually, there are 3. So first, let's talk about Allpair shortest path problem. The problem says, I'm given a graph. It may be directed, it may be undirected, but I want to find the length of the shortest path from any vertex to any other vertex. So I really want to build a matrix of values where the rows correspond to the vertex source, and the columns correspond to vertex destinations. And you want to know what's the length of the shortest path from A to B. So think of this as your matrix of distance values. The simplest way to do this is to simply run Dijkstras n times from each of the source vertices. So eventually you'll get all the right answers, and the time complexity for this is m. So it's going to be simply n times whatever it was before, which was m plus n log n. So when you multiply by n, it becomes mn plus n squared log n. Now, instead of doing this, there may be a better way to do it if the number of edges is very large in the graph, and that's what we're going to look at next. That's what is called as Floyd-Warshall's algorithm. Floyd-Warshall's algorithm is quite simple, but in order to understand this, it kind of helps to look at a few other things. Think of a distance matrix as a matrix that looks like this. The rows correspond to vertices. The columns also correspond to the same vertices. Now, the diagonal is always going to be 0 because the distance, the length of the edge from any vertex to itself is of length 0. Any pair of vertices that are not connected by an edge, you'll see those set to be infinity. So infinity simply says, yeah, these 2 don't have an edge connecting them. And so we're just going to write those as infinity, which means from from vertex 2 to vertex 1, there is no edge. That's what this infinity means. This 3 here means that there is an edge of length 3 going from vertex 1 to vertex 2. This says there is an edge of length -4 from vertex 1 to vertex 5. So for Floyd-Warshall, it's okay to have negative edges. The only thing you have to worry about is that you have to make sure there are no negative cycles. So as long as there are no negative cycles, Floyd-Warshalls will work for you. So think of this as the distance, as the lengths of the edges. So if you have a graph with 5 vertices and the edges are shown here and the weights are shown here, then you would end up with essentially a distance matrix. But these distance matrices are the distances if you were to use only one edge. That's why it's called D0. D1 is D1 is the distance when you use at least how does this work? Right. So here, these are the distances if you were to use a path of length just one, namely just the regular edges. You know what? It's probably better I explain this to you next time, because I have to show you how a matrix multiplication gives you a distance measure. And it's probably a good idea for me to show you a detailed example, and it's not here, so it's probably not a good idea to discuss this. Instead, let's take a look at Floyd-Warshall's algorithm, and let me show you how this. So Floyd-Warshall's algorithm turns out to be something very, very simple. It says, this is the code, this is the algorithm here. There are 3 for loops. It says for k equals 1 to n, I equals 1 to n, for j equals 1 to n. And there is only one statement here that says if Cij is greater than Cik plus Ckj, then update it. This simple algorithm turns out to be enough to get the length of the shortest path to any pair of vertices, assuming that you start with a distance vertex. And this distance vertex is this D0 here that says what are the edges in the graph. I'm going to stop here today, but I'm going to explain to you next time why this works and why this is an example of something called dynamic programming. And also in the process, I'm going to explain to you how this second version of Dijkstras also works out. I'll also show you how this turns out to be equivalent to something called matrix multiplication. So why don't we wait to do that the next time? For now, it would be a good idea for you to go back and focus on Dijkstras, make sure you understand this well. And I'll give you some problems on Saturday to work on with regard to Dijkstras. How does that sound to you?
Yeah, sounds good.
That sounds good.
All right. So let's postpone that our discussion to next week for Floyd-Warshall. Okay. Any questions about what we covered today? No questions. Okay. So then let me stop sharing.